Hey guys, today we're doing Chapter 10, Sections 1 and 2. And I've grouped them together because they pretty much just build right off each other because we're just talking about the binomial probability distribution functions, and then we're going to talk about standard deviation and variance for those types of functions. Alright, first thing we have is our binomial probability theorem, which just tells us what does it mean to be a binomial distribution. So in a binomial experiment with n trials, the probability of success is p in each trial, and the probability of failure is q, which is equal to 1 minus p. In other words, it's the complement of the probability of success. Then we can say that the probability of exactly k successes is going to be n choose k times p to the k times q to the n minus k. Hopefully you recognize this formula from the last chapter we did. It's the same exact thing. We're just focusing on these probability distribution functions in the context of a binomial experiment. Okay, this season Al Horford leads the NBA in percent of baskets made at 63.7%. Consider the situation where he takes 5 consecutive shots. Let x be the number of shots made in 5 attempts, and let p of x be the probability of making x shots in 5 attempts. We want to complete the probability distribution table. So the first thing we're going to do, we're going to write the formulas up here, and then we're just going to create the decimal down here. So I'm going to start by figuring out what my n, p, q, and k values are for each of these. Okay, so my n values, that's how many shots I take, so I'm going to say that's 5. P value, that's the probability of success. So they're saying that he makes 63.7, so this will be 0.637. So that means that Q is going to be 0.363 because that's the complement. And then K, well, our K value changes. So in this one, K is 0, 1, 2, 3, 4, 5. Okay, so our K values are changing. So for this first one here, I start with n choose k, so this will be 5 choose 0 times 0.637. How many successes did I have? 0 times 0.363. How many failures did I have? 5. Okay, this one, same thing. So I start with 5 choose 1. 0.637, I had 1 success, and I had 4 failures. Okay, this is 5 choose 2. I had 2 successes, and I had 3 failures. 5 choose 3. I had 3 successes and 2 failures. 5 choose 4. I had 4 successes and 1 failure. And then in this last one, 5 choose 5, and I had 5 successes and 0 failures. Okay, so now I can plug those into my calculator. And this first one, I get 0.0063. Next one, I get 0.0553, 0.1941, 0.3406, 0.2988, and 0.1049. Okay, so I've created my probability distribution table. So these are my x values, or the values of my random variable. These are my p of x values, or the probabilities for each of those random variables. Now I want to sketch a graph for the probability distribution. Well, my x values, those are my random variables, so I'm going to start with 0, 1, 2, 3, 4, 5, because I had 5 shots made. On my y-axis, I'm going to use my p of x values, and they went from about 0 to, looks like my highest one was 0.34, so I'll just go up to 0.4. Okay, so graphing this distribution here, for 0 I had 0.0063, so that's pretty much down here at 0. For 1, I had 0.0553, so that's about here. For 2, I had 0.19, which is at about 0.2. Then I had 0.34. And then I had 0.29. And then 0.1. So this is approximately my probability distribution graph here. Now we've got some questions to answer. What is the most likely outcome when Horford shoots 5 shots? This is called the mode of the probability distribution. Well, if I look here at either my table or my graph, I can see that the highest probability is going to be this point here, or this point here, and that happens when I shoot 3 shots. So 3 is the most likely outcome. Okay, 3 shots made. So that means that this is the mode of your probability distribution. If Horford took 10 shots instead of 5, what would you suspect would happen to the mode? Well, hopefully you say that it would become 6 because it would double. And if you think about it, remember that the probability of him making a shot is about 63%. So if he made 10 shots, he should make approximately 6 of those shots if you were having an accurate probability. Okay, so it would double. Okay, using our formula from chapter 7 below, find the expected value or mean of the probability distribution. Remember that x sub I is the value of the random variable, p of x sub I is the probability of the random variable. So again, we're finding that expected value that we found back in chapter 7, and the formula looks nasty, but it's really not that bad because we're just taking each of our random variables times our probability of that random variable, and then we're adding them all together. So looking back at my table, for my first one I had 0 was my random variable, and the probability for that was 0.0063. Okay, then I take 1 times 0.0553, and I take 2 times 0.1941. And then 3 times 0.3406, 4 times 0.2988, and 5 times 0.1049. So if I add all those together, I get 3.185. So that's my expected value, which means that it's expected that I make approximately 3.185 shots. Okay. Now on to section 2. Section 1 was just kind of a review of your binomial probability distributions, which we've already talked about. Section 2, we're going to actually talk about some things that we can do when we have a binomial distribution. So the mean of a binomial distribution is represented as mu, with n trials, and probability p of success on each trial is given by mu equals n times p. So in other words, if you have a binomial situation, you can always find the mean by doing n times p. So the number of trials times the probability of success. So let's just think about our last situation. We had n equals 5, and our probability of success was 0.637. So if I take 5 times 0.637, hopefully you'll notice that I get 3.185. Okay? So this is just another way of calculating that expected value, except it's a lot easier when you have a binomial situation. Okay. Next up, variance and standard deviation for a binomial distribution. In a binomial distribution with n trials, probability p of success and probability q of failure on each trial, the variance, which remember is sigma squared, and the standard deviation, which is just sigma, are given by sigma squared equals n times p times q, and sigma equals the square root of n times p times q. So remember that the relationship between standard deviation and variance is that if you take standard deviation and you square it, you get variance. If you take variance and you square root it, you get standard deviation. Okay? So that's why standard deviation is represented as sigma, and variance is represented as sigma squared. So whenever you want to find standard deviation and variance for these, it's really easy because you just have to know NP and Q. So remember that in this case we had N equals 5, P equals 0.637, and Q equals 0.363. Okay, so if I take 5 times 0.637 times 0.363, that should give me my variance. And when I do that, I get 1.156155. Okay, so that's my variance. And then remember that to find your standard deviation, you can just square root your variance. So I can just take the square root of that variance that I just got, and that will give me approximately 1.0752. Okay, and that is everything for sections 1 and 2.